Did you know that geologists might be able to tell where you went on vacation just by analysing the sand stuck in your backpack? And without ever actually seeing that sand.
What are you going to do that based on?
X-ray diffraction.
A method that uses a so-called XRD scanner. You put in finely ground soil and sand samples, and it returns a graph like this. Apparently, such a diffractogram reveals exactly what minerals are inside the sample. Online mineral libraries, containing data on over 10,000 different minerals, can help to identify what's there. The elements that show up depend on the environmental conditions the sand has been exposed to. Arjan Dijkstra is an earth materials specialist, meaning he creates a lot of these scans.
Typically 100 a year, so not huge numbers, but I've also seen lots of these scans that other people collected. Yeah, often students come to me with scans.
Let's just say crazy numbers. So here's the real test. Has he become a living version of the mineral library? One that can not only identify the minerals, but actually determine where they came from.
Interesting challenge, yeah.
That's what we're about to find out in this series.
Let's go.
Okay.
In this episode, we're diving into how we get from this, the sand we accidentally brought back from our holidays, to these diffractograms that will eventually present to Arjan. What is it that we are seeing on these graphs?
So any material, any rock consists of different minerals and they all have a different crystal structure. And these minerals we can identify through that crystal structure with a method called X-ray diffraction. And that's what's showing us these peaks in this diffractogram.
And what really happens behind the closed door of this machine?
The magic that happens in there is quite interesting. So there's a very, very powerful X-ray source. It sends out waves of X-rays onto these materials. And these X-rays get reflected by the crystal lattice planes. Now, that happens all the time, but if you shine that X-ray source at exactly the right angle onto a crystal lattice, then you see that all the reflections coming off the crystal planes, they are in phase, as we say. They are showing what we call constructive interference. Now, the best way to illustrate that is imagine you have two people playing an instrument on a stage and they are perfectly tuned, so they're playing exactly the same note. That means that the waves of sound they're sending out have exactly the same wavelength. Now, depending on where you are on the stage, these waves coming from the two instruments on the stage can start to interact with a way where suddenly you hear the sound very, very loudly. That's called constructive interference or resonance. They can even interact destructively. Actually, the sound can completely disappear. That's what happens in noise-cancelling headphones. Now, this also happens in an X-ray diffraction instrument. If the conditions are exactly right, if the angle in which you shine the X-ray on your material is exactly right for that crystal lattice, then suddenly you see a peak in the reflected X-rays. And that means that it's scanning across. What it's actually doing, it's scanning, the X-ray source is here and the detector is here. It's changing the angle, and suddenly at a certain angle you see, bang, you see a very strong signal. And that's what's showing us these peaks in this diffractogram. And that tells you something about the crystal lattice of that material. And those peaks, the angles at which they occur, on the horizontal axis on the scan, you see the angles at which it scans. Where those peaks occur, they tell you that's crucial information to work out what material is in there, what mineral is in there, what structural compound is in there, as long as it has a crystal structure.
But using the XRD machine is not a matter of just putting in some grains of sand into the sample holder. There's an advanced sample preparation process that we will break down for you in the final episode, which includes the grinding of the samples. But why is that so important?
You want to have a nice homogeneous mixture. You want all the minerals to be present in the little scoop of material that you pick. So that means that you have to grind it really fine so that all the minerals from that rock, the minerals could be centimeter size, or the minerals in the sand could be several millimeters, but you want them all to be present in that little scoop of material that you take. So you grind them really fine. And then you have to make sure that these crystals are present in that little scoop of material in all kind of orientations. So if you can imagine that you have a flaky mineral, then you don't want them to all be aligned, so all flat lying in the same orientation, because then you don't get the full information that you need to identify these minerals. You need them to be, if you have a flaky mineral, some need to be like that in the sample holder, some need to be like that, some can be flat, and you only achieve that if you make a really, really fine mixture, so the sort of consistency of flour. Then you have a grain size, a particle size that guarantees that all the orientations are present, if you like.
Katrin helped us to carry out this procedure with extreme care, which resulted in these diffractograms that we're about to show Arjan. If you're curious to find out if he can deduce the origin of the sand based on these scans only, join us for the next episode, where we will show Arjan the diffractogram of this orange sand.